Hello, my dear students. Welcome to today's class. In yesterday's class, I have started FET. So, what is the FET? It is a three-terminal, unipolar, voltage-controlled semiconductor device. This is about the definition we have studied with the JFET, otherwise the FET, and then we saw the classification of FET, that is junction FET, JFET in MOSFET, and again in MOSFET enhancement type and depletion type, and JFET, and each type of MOSFET enhancement and depletion is having two types, that is N channel and P channel. And we have also discussed the comparison, otherwise the differences between BJT and FET in yesterday's class, and also the topic important for exam what I have discussed yesterday is the construction of N channel JFET. Okay. So today, construction of N channel JFET. So today I will be continuing the class with the further topics. So I am just giving you a brief revision about the construction of N channel and the P channel JFET because it is very important for exam point of view. So what I have told in yesterday's class, and I want to add one extra point there. So what I told you, N semiconductor bar and two P-type bars. Gate is formed with internally connecting the two P-types and two ohmic contacts are taken from either sides of the N semiconductor bar as a drain and source. This is gate which is internally connected, right? So what I have told about the P bar, this is P type semiconductor, right? Which I have told you that it is heavily doped. It is heavily doped, okay? And this N substrate, otherwise the N type, is lightly doped. It is lightly doped, okay? So, N semiconductor bar, this forms PN junction here. Two PN junctions are formed, and the space between the two PN junctions is called as channel. Everything I have told you yesterday. Okay. Now, what I want to add here is the formation of depletion region here. A little small amount of depletion region will be formed along the PN junction. This concept of depletion region you have already studied in the diodes, where the two ends of the substrates touch each other is called as the junction, and because of the process of diffusion, that means the nearby the electrons and holes near the junction will combine with each other to form immobile ions. Okay, that process of crossing over the junction by the electrons and holes without any external electric field is called as diffusion. Okay, and because of the process of diffusion, what happens? Immobile ions are deposited near the PN junction, and that is called as the depletion layer, otherwise the depletion region. So two depletion regions are formed here. Okay, and this depletion region avoids the further pass of the electrons or holes across the junction, formation of the depletion region. So here also as there is existence of two PN junctions, around the PN junction, two depletion layers are formed in the JFET. Okay, here we will consider N channel. So same thing happens with the P channel also. There also, what happens? The junction will be the depletion layer will be formed near the N type substrate, otherwise the PN junction there. Here this is P type substrate, right? Here this is the junction. So near the junction, what happens? Depletion region, otherwise the depletion layer is formed. Same depletion layer will also be formed in the P type. Same concept is applicable there also. So this formation of depletion region occurs on both the sides. Okay, this is what I wanted to add in the what we can say construction of the N channel JFET. Okay, formation of the depletion region near the PN junction. Now we will move with the further topic. That is the what topic is there for today's class is the working. Before that, I will move I will tell you little about the terminals. Okay, terminals. Terminals of what? JFET. Now we are moving further with only JFET, not the other types of FETs. We are moving to the JFET, and in general, I am discussing the working and the construction. We are considering always N type. When it comes to P type, we have to assume that the opposite operation will be taking place. So further topics I will deal. Moreover, I will stress on the N type JFET only. Okay. So JFET terminals of JFET. What yesterday only I have given the names, so you people are already aware with the names. That means drain, source, and gate. Okay. So now the definition: source, drain, and gate. Okay. Source. From the name itself, you can imagine that it is the source for something. Source, what we basically mean by source is that is supplying something, that is able to give something to somebody, okay, for their usage. Okay. So, what is this source here? Here the source is the source of charge carriers, otherwise the majority charge carriers we can say. So, source gives the majority charge carriers. Okay. Drain. Drain means which will eat up, otherwise which will absorb everything. It will going to absorb everything. It is just, you can imagine, it is like a what we can say is a water drain, from where the water is going to pass away. Okay. And gate. Gate is the control. Gate is the control that is going to have a what we can say control over how much charge carriers are passing from source to drain. Source will give the charge carriers, drain will take, and how much is passing from source to drain is controlled by the gate. Simple concept. Okay. So in particular, if we are going to define the source, how we will define with respect to the JFET is that it is the terminal, right? It is one of the terminals. Source is one of the terminals of the JFET. So source is the terminal that, otherwise it is the terminal from where majority charge carriers, okay, as we have already discussed yesterday that it is a unipolar device, only majority charge carriers contribute to the formation of, otherwise conduction of the current. So it is the terminal from where majority charge carriers enter into the silicon bar. Otherwise, we can say, if we are talking about specifically N type or P type, N type or P type bar. In case of N channel, N bar, N type bar. In case of P channel, P type bar. Okay. The terminal from where, that means it is the starting point for the charge carriers to start travel. Is the terminal, it is the terminal from where majority charge carriers enter the bar. That means this, the channel from where it is going to enter the channel. So this is the starting point for the charge carrier to start their journey towards the drain. Okay. Next, so drain is going to what? It's absorb, otherwise it is going to take all the charge carriers. So how we can define it? The terminal through which the charge carriers leave the bar. Leave the N type or P type bar. That means the exit point. This is the entry point, source. Gate. The terminal that controls the flow of charge carriers. Carriers from source to drain. Right? So these are the three major, what we can say, terminals of the JFET, where the terminals are named as source, drain, and gate. Okay. Source, the point, otherwise the terminal from where majority charge carriers enters into the silicon bar. Drain, from where they will leave the N-type or P-type bar. Gate, the terminal that controls the flow of charge carriers from source to drain. So, any potential electric field or electric potential applied to the gate is going to control the flow of electrons from source to drain in case of N channel JFET. Okay, these are the three terminals of the JFET. Okay, and very important, this question can be asked for 1 to 3 marks. In 1 marks, they can just ask you to define the source terminal of the JFET. Then you have to write the definition for source. If drain is asked, you have to write for definition of drain. And if gate is asked, you can write the gate also. And this construction, what I have discussed yesterday, this construction questions is many times asked in the question paper. So it is very, very important. The symbol is very, very important. The classification is also very, very important. These questions are asked for the from 1 marks to 2 marks to 3 marks. Any type of question can be asked. Only for 1 marks means just a symbol could be asked. For 2 to 3 marks, classification can be asked. For 3 up to 3 marks, otherwise only even for 2 marks, this construction of N channel JFET along with the explanation can be asked. Even for N marks, N channel or P channel, both type of constructions could be asked. And even the terminals of the JFET can be asked for 1 to 3 marks, right? Next subtopic, biasing condition for JFET. So how it has to be biased for its operation. So I am drawing a circuit for both N channel and P channel here. This is the N channel, these are the 2 P types. Here there is a drain. Here you can see a source. The gate internally connected with both the P's, both the P types. Okay. And this is source, this is drain, this is gate, this is source. Okay. So here for the operation of the JFET, you need to connect 2 types of voltages. which are named as VGS and VDS. The voltage across gate and source, one of the voltage has to be connected across gate and source, and the other voltage has to be connected across drain and source. And depending on the voltages, the two voltages, the operation of the, otherwise the flow of the electrons through the channel can be controlled with the application of these two voltages. Okay. So what we are controlling here, we are controlling voltages, that is in turn controlling the current flow from the across the N channel. That's why it is a voltage controlled device. Okay. We are controlling the flow of electrons through the channel from source to drain. Electrons will flow from source to drain, and that how much electrons flow from source to drain is controlled by the two voltages, VGS and VDS. That's why it is a voltage controlled device. Okay. So for the biasing, there is one condition for the biasing of JFET, that the VGS, the voltage across the gate and source, has to be connected such that it will reverse bias the gate. This is NPN type, right? So this is P type substrate, so it has to be connected to negative terminal of the battery, reverse biasing. P type is connected to negative terminal. This is called VGS. Okay. The other voltage is connected like this. This is the biasing condition for N channel. N channel JFET. Okay. Here also I will show the depletion region because it is always existing. With the application or without the application of the voltage source, depletion region will be there, but with the variation in the voltages, this depletion region itself is depletion region is controlled, and as a result, the electrons flow can be controlled across the JFET. Okay. So the circuit for the P channel now, the biasing condition diagram for the P channel. Depletion region, the gate, drain, source. Voltage across the drain and source, and one of the voltage across the gate and source. Okay. Now this is N type, so it is connected to the positive terminal of the battery. This is N type because it is a P channel. Okay. So here the source is also, the VDS is also inverted. VDS. Here this is also VDS. N channel, P channel. Okay. So the biasing condition says that VGS has to be connected to the JFET such that it will reverse bias the gate terminal. Gate terminal should be always reverse biased. Okay, for the control of the depletion region, in turn control of the flow of electrons through the channel. Okay, so this is about the what? Biasing condition. Next, the working of N channel JFET. Now we'll see the working. Now we'll see what? The working. Working of. This is also very, very important for exams. Working of N channel JFET, otherwise JFET. So biasing conditions, we are already aware that the VGS has to be selected such that the gate terminal is always reverse biased. In the working, there are two conditions, two cases. The first case, case 1, when VGS is equal to 0. Okay, VGS is equal to 0. VDS is increased gradually. Increased gradually. Gradually means what? Slowly, step by step, the value of VDS is increased, keeping the VGS at a constant value, that is 0. Okay. So how the circle appears? So we are controlling the operation of the N channel JFET without the interference, otherwise without any contribution from the gate terminal, we are controlling alone by controlling the VDS. Okay. There already exists some depletion region. This is P. This is N. These two are two P types. This is the drain. This is the source. And what is the condition is that we are not connecting VGS. VGS is kept open. Next, we are connecting the voltage across drain to source. This is source, this is drain, and this is variable which is gradually increased in steps. Okay? Gradually increased in steps. So as VGS is not applied any voltage, we have set VGS is equal to what? 0. So this depletion region does not depend on the voltage VGS now. Before going to the N channel working, I just want to highlight a very important point, that the operation of the JFET, that means totally the control of the flow of electrons from the source to drain, is completely depending on the concept of controlling the width of depletion region. Okay, controlling the width of depletion region. And the width of the depletion region can be controlled by two voltages, that is VGS and VDS. Right? So here we are considering two cases wherein we have kept VGS as 0 and we are varying VDS. Okay. Next case we will see that it is kept constant and it is varying. Okay. So we are just checking how we can modify the width of the depletion region. In turn, how we can control the flow of electrons from source to drain. Right. So here the total concept is to control the electrons flow from source to drain, and that can be controlled by controlling the width of the depletion region. And how the depletion region width can be controlled? That can be controlled by two types of voltage, that is the voltage across the gate to source and voltage across drain to source. Okay. These two voltages, VGS and VDS, are responsible for the width of the depletion region. And the width of the depletion region has the effect on flow of electrons. Okay, so here we are considering the first condition wherein we have considered the VGS to be 0. Now VGS is 0, and we are starting the value of VDS from 0. Initially it is 0. So what is happening here? As it is 0, the depletion region is the default depletion region. Default depletion region means the depletion region that is already existing because of the nearby electron and hole reformation and the immobile ion formation and depletion region under unbiased condition. When the JFET is under unbiased condition, already existing depletion region is there, and that depletion region is very thin layer. So what is happening? The space between the two PN junctions is wide, comparatively wide, and more space is there for the electrons to release from the source and to reach to the, what we can say, drain. It will, what we can say, start from the source and they can easily travel towards the drain because there is enough of space for them to travel, because the depletion region is a very thin region and leaving enough of space inside the channel for the electrons to travel from source to drain. Okay, as simple as that. This has to be wide. If this is wide, electrons will flow easily from source to drain. So initially what happens, when for the low values of the applied voltage, electrons start traveling. Electrons will move towards the drain. Electrons are moving towards the drain, but the conventional current is shown in the opposite direction. That is the ID. So, because of the flow of these electrons, what happens? Because the flow of these electrons, current is constituted, and that current is called as the ID drain current. Right? Without the application of the gate, enough of space is there because the depletion region is not spread too much. It is in its initial stage. It is existing, but the space, the channel width is enough for the electrons to travel easily from source to destination, and they are freely moving towards the destination. And when electrons are moving from source to destination, current, the ID is formed. Okay. Now, when we increase the value, as we keep increasing the value, what happens? As the voltage is increasing, current will increase. So here, this channel, this particular N bar channel is simply acting as a resistor. It is simply acting as a resistor that follows the Ohm's law. That means with linear increase in the voltage VDS, corresponding change in the current is observed. Linear, both are linearly increasing. Okay, with increase in the VDS, ID is increasing. As a result, what happens? The voltage will start dropping across the junction. Okay, that I am going to show you. So here, this is the P type. This is kept open. Voltage is applied across the drain and the source. This is drain. This is source minus plus. So what I told you, electrons have started traveling from source to destination. Linearly, current will increase obeying the Ohm's law. As the voltage is increasing, current is increasing. So as it is obeying the Ohm's law, the channel, the N channel is simply behaving as a resistor. It is just behaving as a resistor. Okay, I'm just representing it by resistor. Right? Okay. So as it is behaving as a resistor, it is nothing but a resistor now. So what happens in a resistor? Voltage drops. When there is a resistor, voltage drop takes place. For example, let me consider that I have applied 4 volts. So voltage starts dropping from each at each point of this channel, behaving as a resistor. See, now this channel is behaving as a resistor. It is not a discrete resistor. It is not a separate resistor, but its character is now like a resistor. So what happens now? 4 volts is dropped here. The next point 3 volts will be dropped. The next point 2 volts will be dropped. Okay. And if I take another resistor here, 1 volt will be dropped, and finally 0 volts. The entire voltage is dropped in steps. So as we can observe, more voltage is dropped across the terminal D, whereas less voltage towards the source. Now because of this drop in the voltage, the depletion region starts expanding. this depletion region starts expanding gradually with increase in the voltage. So it is expanding like this. Okay, it is expanding like this. And it is expanding more towards the drain because the potential towards the drain is more and the potential towards the source is less. So the what we can say depletion region has expanded more towards the drain. Okay, and here also in the depletion region, the depletion region is spread towards the N channel because it is lightly doped. Whenever the lightly doped substrate is there, otherwise the silicon bar is there, if the lightly doped, the depletion region penetrates more towards the what we can say lightly doped region. P is a heavily doped, that's why the depletion region is almost a very less spread towards the P. I missed this point. Note down this point that depletion region penetrates, otherwise it is having more effect towards the lightly doped region of the silicon bar. Okay, as I have told you, N is lightly doped, P is heavily doped. The depletion region inside the P will be comparatively less spread as compared to the N. That's why more depletion region is spread towards the N. Like here, likewise the depletion region is expanding towards the N channel here, and P inside the P it is not spreading much because it is heavily doped and it is lightly doped. The N bar is lightly doped. The depletion region is entering towards more towards the N type. Okay, and it is spread towards D more compared to, that means the drain terminal more compared to source, because the drain terminal has a higher voltage drop. And this depletion region expansion, otherwise the widening of the depletion region has become because of the voltage drop across the channel. Okay, and that happened because the channel is now behaving as a resistor. Okay, I will come again. I will repeat the concept. Voltage is increased. As it is gradually increased, electrons start flowing from source to drain. Now it is simply the linear relation between the VDS and ID that obeys the Ohm's law. As it is obeying the Ohm's law, channel simply reacts like a, otherwise it is acting as a resistor. As it is acting as a resistor, definitely voltage drops will occur. These voltage drops are starting from the drain, that means a higher voltage drop across the drain and the least voltage drop across the near the source happens. Okay, so near the drain more voltage drop is there, so more depletion region expansion is towards the drain. Okay, so this happens here, right? So what is happening? Because of the more voltage drop towards the drain, depletion region has expanded more towards the drain. And what happens? They are come very close. The depletion region has come very close. Compare this and this. The space is more, electrons freely travel from source to destination. The space has become very, very narrow, but it is not touching. The space, the two depletion regions are not touching each other, but the space has become very narrow. This condition is called as pinch off. Okay, what it is called? Pinch off, and this is very, very important. Frequently asked question, explain, otherwise define pinch off voltage. Otherwise, just the concept of pinch off, what it is. So what is happening? The two depletion regions have come very close without touching each other. They have come very close, and this condition is called as pinch off condition. This condition is called as pinch off condition, and the value for which this occurs is called as pinch off voltage. What it is called? Pinch off voltage. Okay, which is represented by V. Okay, here region are coming closer to each other for some application of the voltage. Okay, here the value is 4 volts. It can be any other volt. Okay, any other value of the voltage. So for the value, for the voltage for which this condition of pinch off is occurred is called as pinch off voltage. And when it occurs, when they come very close. Now what happens? They are not completely touching each other. The channel is not completely blocked. Channel is not completely blocked. Still, there is space, but the space is very, very, very narrow. Right? Once this pinch off occurs, what I have shown here, ID now becomes constant. And that constant value of ID is called as IDSS. Okay? For the value of Vp, that means pinch off voltage, where ID has become constant, is called as the constant value of ID is called as IDSS. Okay, so what is IDSS? IDSS is the value of ID value, otherwise it is the value of constant drain current for the condition of pinch off is called as IDSS. Okay, so we'll write down the important definitions here. Okay. So pinch off is a condition in JFET where depletion regions okay come very close to each other, without touching each other. Okay, where value of drain current ID becomes constant, and this value is called as IDSS. Okay. Pinch off is a condition in JFET where depletion regions come very close to each other without touching each other, where value of drain current ID becomes constant. Is called as condition for pinch off. Okay, right? The voltage for which the pinch off condition occurs is called pinch off voltage. Is called what? Pinch off voltage, represented by Vp. Okay. So where we have reached, taking the VGS as 0, increasing the value of VDS constant. So initially the channel was wide enough, the electrons were freely passing. When the electrons are passing, they constituted a current that is called as drain current ID. Okay, so that ID is linear with the application of VDS, that is obeying the Ohm's law. When it obeys the Ohm's law, then the linear characteristics say that the channel is behaving as a resistor. Okay, when the channel is behaving as a resistor, the voltage drop across the channel takes place, and more voltage drop occurs towards the terminal D, that means the drain terminal, comparing to the source terminal. Okay, as a result, due to this voltage drop, what happens? The depletion region starts widening, otherwise it starts spreading, right? And it spreads more towards the drain. It is spreading more towards the drain, comparatively spreads less towards the source. As a result, what happens? It will form the shape of what we can say wedge. Okay, wedge shape, okay, which is like this. Okay, the depletion region is closer towards the top and it is less closer towards the as it is approaching towards the bottom, right? But the two depletion regions are still not touching each other. The two sides of depletion region have become very close to each other, but they are not touching each other. This particular condition is called as what? Pinch off condition. And for the voltage for which this happens is called as the pinch off voltage VP, right? So all this I have discussed. Now what happens further? Once it has reached the pinch off condition, we are still increasing the applied voltage VDS. Now we are still increasing the applied volt VDS. What happens? Immediately after the pinch off occurs, the voltage ID has become constant and that constant value is called as IDSS. Right? Now it has become constant, we are applying more voltage. Up to some extent, it will maintain the value as constant. Right? But we are going beyond that value. Still we are applying the value. Then what happens? Avalanche breakdown takes place. Okay. Pinch off occurred. ID value became constant, and for which value of voltage it has become constant is called as the VP. That means pinch off voltage. Everything is clear up here. But we are what we are doing? We are applying more voltage. It will bear up to some voltage. It will maintain constant value. But beyond that voltage also, if we are applying, what happens? What I told you, avalanche breakdown. Avalanche breakdown takes place. Avalanche breakdown takes place and suddenly ID increases. Suddenly ID increases as a result of what? Breakdown. Okay, and this particular voltage is called as breakdown voltage of JFET. Breakdown voltage of JFET. This breakdown happens at the breakdown voltage of JFET. Okay, suddenly ID increases. Right. This is about the working of N-channel JFET with the condition VGS is equal to 0 and gradually increasing the value of VDS. Right? So it started with just a passing of the current where the channel behaved as a resistor, voltage drop occurred, voltage is dropping more towards the drain. So more depletion region spreaded towards the drain. Okay, and because of that, what happens? Pinch off happens, and that happens for the value of pinch off voltage, where after pinch off the ID becomes constant. After the constant value, if we are applying more and more voltage, what happens? Avalanche breakdown happens. Suddenly the ID increases. This happens for the breakdown voltage of the JFET. Okay. So this is about the working of N-channel JFET for the case 1. Now we will move to the case 2. Now I am moving towards the case 2. Now, case 2, VGS is varied, and VDS is set to varied. VDS is constant. Constant means not zero, because zero means it will not start conducting. For the conduction, VDS has to be set to some specific value for the conduction. Okay. So how the circuit appears now? Some depletion region is already existing here. The VDS is set to some constant value. Making this minus n, plus that will reverse as the gate terminal. This much depletion region is already formed. This is the default depletion region that is resulting due to what? The process of diffusion near the PN junction. This is PN channel. This is having some constant value, whereas this is increased. Now this is variable, right? Now what happens? We have studied that under reverse bias condition, any diode with application of reverse voltage, the depletion region expands. So here we are applying a reverse voltage to the two PN junctions. So as a result, what happens? Depletion region starts expanding itself. It will start expanding itself. It will start expanding itself. Okay. So what happens here? With the application of the VGS. Initially VGS is 0. That means the depletion region is spread to the minimum, the least value. As we are increasing the VGS value, what happens? It keeps on spreading itself and the channel starts shrinking. So as we are increasing the reverse voltage, the channel width is decreasing. With the increase in the reverse voltage, as we are increasing VGS, that means minus value. Its value in terms of minus, that means it is 0, then it will become minus 1, it can become minus 2, it can become minus 3, minus 4 and so on. As we are increasing the negative, the reverse bias voltage for the VGS, the channel width is decreasing. Channel width is decreasing as a, channel width is decreasing, but the depletion region is expanding. Depletion region is increasing, channel width is decreasing. As the depletion region keeps on expanding itself, then what happens? The space is keep on shrinking. So what happens as a result? The electrons that are flowing from the source to drain, those will be restricted and there will be drop in the value of ID. ID will decrease. Reverse voltage VGS increases. As a result, channel keeps the channel width decreases as the depletion region expands. As it is decreasing, the drain current ID decreases. Right? Here also something happens, that is for the value of VGS, where it will become equal to or greater than VT. That means the pinch off voltage. Pinch off voltage of the other concept, where pinch off is the value of VGS, for which the depletion region have come very close to each other, right? Very close to each other, but not touching each other, where the ID becomes constant. Here what happens? When the VGS becomes greater than or equal to VT, that pinch off voltage, the two depletion regions touch each other. They touch each other, making the channel completely blocked. Channel completely blocked. No further electrons will pass from the source to what we can say drain. No further electrons will pass from source to drain as a result of VGS becoming equal to or greater than what? The value of pinch off. The two depletion regions completely touch each other, blocking the channel, avoiding, otherwise blocking the further electrons to pass from the source to the destination, right? This is called as VGS off. The voltage for which this particular thing happens is called as the VGS off, and this is called as the cut off. This particular concept is called as the cutoff, and this voltage is also called as cutoff voltage, which is represented by VGS off. No further current flows. Very small amount of current will be flowing because of the minority charge carriers. Reverse saturation current, what we have studied in the previous concepts, also in the order of nano amperes. Very small in the form of nano amperes, that means 10 to the power of -9. That much current will be flowing through the channel, right? So the ID has become now almost ID is almost equal to 0. Okay, approximately or almost equal to 0, and this is called as VGS off, otherwise the cut off condition for the JFET. Okay, so what all we studied here? Taking the VGS as 0, VDS, there we see many concepts, that is cutoff voltage, the breakdown voltage, everything. Here, keeping the VDS as constant, here VDS is just to constitute the current due to the flow of electrons from the source to destination. Some external voltage has to be applied for the electrons to travel from the source to destination, forming the current ID here. Okay, it is the same as the previous case, but what is happening here is normal current ID is flowing, but the flow of that current ID is controlled with the reverse voltage VGS. Okay, considering the VGS initially be 0, electrons are easily passing through the channel and the current is at its maximum value ID. When we increase the reverse voltage, applying the voltage as -1, then what happens? The channel, the depletion region expands. The channel has become little less wide. Okay, it has shrinked now, little. So what happens? ID has decreased. We are further applying the reverse voltage. We are increasing the reverse voltage. Again, the depletion region expands. The channel becomes more narrow, and it will again decrease the value of ID. As a result, what happens at certain stage, a certain value of VGS, that is equal to VP. When the VGS value becomes equal to VP, the channel completely touches each other. The channel is completely what we can say blocked, and the two depletion regions from the both sides touch each other. Depletion regions are almost in contact. Okay, so as they are almost in contact, the channel is completely blocked. The channel is not allowing further electrons to pass through it, right? This particular condition is called as the cutoff condition. That happens for the VGS is greater than or equal to VP, and that particular voltage is called as VGS off. Okay, otherwise VGS cutoff. Okay, this happens with the value for VGS is equal to or greater than VP. Now what happens? No further electrons will pass through the channel, and the ID almost becomes a 0. ID is becoming almost is equal to 0, and it happens for the cutoff voltage of the JFET, and this particular voltage is called as the cutoff voltage of the JFET. Okay, ID has become almost equal to 0 now. Okay, ID has almost become 0, but what is observed is that very small amount of current in terms of nanoamperes will pass through the channel, will be existing there, and that is due to the reverse saturation current, and that is the reason for the minority charge carriers. Okay, this is about the working of the N channel JFET, wherein we have considered two cases. Both the cases in detail I have explained you here. Okay, so one more point we can observe here is VGS and VP are having same value. VGS and VP are having same value, but The only difference is that VGS will be having the value in terms of negative, and it will be having the value of value in terms of positive sign. That means if we there we have considered that VP was 4 volts, so VP is equal to VGS. So VGS will be also 4 volts, but it will be minus. Okay. So VGS and VP are having same magnitude. Same value with different polarities. Okay, minus and plus. VGS is minus, whereas VP is plus. Same magnitude, opposite polarity. VGS and VP. Okay. So this is about today's class, where we have discussed detail about the working of N-channel JFET. Before that, I have added something in the construction of the JFET, where I have told that there is existence of the depletion region. That is because of the diffusion process happening near the PN junction, that will form the depletion region, right? And we have discussed the 3 terminals of the JFET: source, drain, and gate, the definitions. So I proceeded with the working of the JFET. Tomorrow I will deal with the characteristics, the 2 characteristics of the 2 types of characteristics of the JFET, along with the circuit, the graph, and the detailed explanation. So this is about today's class, students. Thank you.